Hi. Yeah, so sorry, I'm not very well actually, so I would have brought some demos. It's just been a bit of a rough couple of days. Just got a cold, but I'm just not feeling the best. And I travelled on Friday, so I'll apologise. I'm from the UK, so it was a pretty miserable day on Friday. And I like to think myself a fairly inclusive and open person, and it's sad times at the moment. But anyway, we'll move on for that. And so I'm going to talk about, and I would have had some demos and played some music for you, but yeah, about a project that I've been working on for a while. I'm at the University of West of England with some PhD students of mine. Some of them are musicians and composers, some of them are computer scientists, and we kind of have this mixed collaboration group. And in particular, we've got this music project which is looking at kind of materializations of musical controllers in particular, but also DSP code and everything and stuff. And although that's more my area rather than some of my students, they're much more interested in composition and in interaction, so HCI stuff. And we've kind of built up this infrastructure that is around physical computing. So a lot of stuff, some of the stuff I'll show you in pictures, is actually building up physical instruments. But the idea is, rather than the musician having to go and buy something off the shelf or more expensive, we want to make them so they could potentially build it. Now, of course, that's not for everyone, I'm not saying that, but the idea of trying to breaking down that barrier of having non-engineers build instruments and things. And, you know, we see software like that, some things like PD or Max MSP, visual programming, is supposed to intensify that, but it's still very much in the programming environments rather than in actual physical computing. And of course, the maker community has broken that down quite a lot still a lot of people who are, tech savvy and things like that, but they're starting to break down those barriers and some things. And so we're looking at that intersection, really interested. And in a minute, I'll flick to that. This is the website where you can find out lots of stuff. There's the GitHub links of all the code. You'll see that it's not just Rust code, and that's what I'll talk a little bit about that in a minute. But my motto is, over the years, I've worked in industry for a long time, it's just use the right thing to solve the problem. Of course, what you think is the right thing is not always what other people think is the right thing, but that's a separate story. And, I'm no more right than anyone else is, so I'm not going to kind of advocate one thing or another. I'll just show you the kind of things that I'm interested in and have been using Rust for. But in particular, I'm really keen on Rust as an intersection with other languages. I don't want it to be the solution for everything, and I don't want the other things I use to be a solution for everything, because I don't think they are. So I just, where it makes sense is what I do. So there's a long history of musical instruments, obviously, and I'm mostly thinking from a Western perspective. I don't at all want to say there aren't many other kind of ways of looking from an entomological point of view about musical instruments. I just don't have that much experience in it, so I wouldn't want to talk about it and present it here. But from a Western place, we've got the kind of classical periods, particularly from kind of around Shakespearean time in my history, where musical instruments started, but particularly since we had the printing press, and music be able to distribute, the kind of musical form of the instrument became quite fixed. The piano didn't emerge first, it was the printing press that emerged, and the ability to distribute music wanted to standardize things. And I'm sure we can all agree that standardization is good in some ways, but it also does hold us back in other ways, and so of course we've got to the modern times, electronics. The 19th century had lots of 20th century, sorry, had lots of bad things caused by many of the innovations, but also had many incredible things. And I'm sure as we work in technology, it's a kind of difficult balancing act. Sometimes I feel that we should just throw it all away, not buy the next phone or whatever, and other times I'm thinking, wow, this is amazing. So anyway, in the UK, we had this thing called the BBC Radio Workshop, which is where they did the Dalek soundtrack, for Doctor Who and all of that sort of stuff, which is famous. And so they started to build these studios. I even managed to get a picture of a woman rather than a guy, which was great. Actually, the Radiophonic Workshop was a real place where actually women had quite a lot of very innovative. Delia Derbyshire is the famous one, but there's a lot of others as well. And of course, in the 80s, we had people starting to break away from the more conventional instruments and finding and being able to make instruments out of other things. Particularly the obvious one is the record deck, and making that into an instrument in its own right. And today we have many people, live coding is a popular thing, and we've got this kind of world of where people are sitting in front of their laptops. And I've been to lots of musical events. It's not that exciting to see people sitting in front of their laptops, but the music they make and the stuff they're using is incredible, right? I'm not a live coder myself, but I love the kind of philosophy behind what they're trying. Really? That's sorry. Yes, you'd think it wouldn't go to sleep when I got it in full screen in Chrome, but it still does. Anyway, I can probably turn it off, but I'm not going to worry about that now. But one of the things we're really interested in, so I'm really interested in using digital synthesis and digital generation of musical instruments, and so how we can connect to these digital devices, but in maybe a less conventional way, not sitting in front of a laptop, but also not sitting in front of a keyboard. And so we're interested in building things. So there's been a lot of work, particularly there's this out of Queen Mary in the UK, there's this thing called the Bella board, which is very much inspired by the Arduino kind of maker environment, but it's got a very high-end, DSP, and particularly the audio, the op amps and all that are, they're non-cheap. It's a very simple board, but you still pay £150 for it because the op amps they're using are expensive, not cheap, and it's a full 24-bit DAC and ADAC and so forth and stuff and things. It's a really nice little board, and it can support, it multiplexes the channels, so you can have full 96 kilohertz kind of speed, but if you want to have 16 channels, you get down to like 22 kilohertz, so depending on what you'll do. But it's really nice, and it's it's a full Linux stack. It's based on a BeagleBone, and they modified the kernel so they can get real time and so forth. And of course, it's a Linux stack, so we can build and compile using our favorite languages, whatever that may be, whether it's C++ or Rust or anything else for that matter. They do a lot of stuff with PD, which is a visual programming language, and things because a lot of musicians aren't going to be programming that. So these are kind of conventional interfaces. I won't spend too long on these stuff, hopefully things. This is the kind of field, the maker field. These are actually all Bella-based instruments that people have built. And most of these are not, not all of them are engineers. Most of them aren't engineers. Most of them are musicians who have just ended up programming for a necessity. Looking at some of their code is, interesting, let's say. But this guy up here, he's built this complete retro drum machine. He completed it, and as far as I know, before he started this project, it took him about 2 years. He'd never had any programming experience at all, and he managed to do it. Stack Overflow helped him a lot and something. It's great talking to him. It's an amazing project, to think that this guy is just a musician that spent all of his time mostly playing analog instruments like guitars and pianos, and then he just decided, he saw a talk on Bella, I don't know, even though probably a kind of conservatory or someone talked about it, and was inspired to build it. And it's pretty amazing that we've made that accessible. Now, he first programmed it in PD, then he programmed it in C. So you can imagine the experience he had. It was not a good experience, and he's great. You can find his blogs. If you can go off my website, you can find his blogs about it, and it's really great to read. And yeah, I think he now complains that he didn't have enough time making music, but anyway. All right. These are the sort of things we are making. I'm not really going to talk about this much. I'm more going to talk about the kind of language side of things and everything, but these are the sort of things. So this is a pressure sensor. So that rather than being capacitive, we have a lot of iPads and stuff and things, people doing capacitive stuff, but it doesn't have any kind of haptic kind of feedback, and so that's a real issue. So we took this pressure sensor and we've worked out different ways of generating musical instruments, or interfaces in particular. They're very much, I'll show you in a second, a separation for it. And up here, for example, these are some 3D printed designs that I've designed. They're connectable. They can be horizontal or vertical, and they connect together with just Lego pieces. But the key thing about it, of course, if I'd brought a demo, I could have shown you, is that they're all based on magnets. So originally I designed them to using a Hall sensor, so you could just detect the magnetic field when they move. But these actually don't have a Hall sensor. They rely on the pressure. But the only reason we're using the magnets is to give the haptic feedback. So the button pops, or the slider, you get just a nice little feel of it actually being resistive, rather than just sticking. And this is a little 2D one, which just drags, it centers back in the center. If the magnet was in, so obviously this picture is taken without the magnet in it, but if the magnet was there, it would be centered, and then you push it, and so you get, so it's very simple, and just literally underneath, they're just felt and things. So the bit that this talk is more about is how do we describe these interfaces in software such that they can be materialized in hardware. And in particular, this is it's made by a company called Sensal in Silicon Valley, and I think they make touchpads, for things like MacBooks and stuff and things. And they have a really nice, it's a UART. They have a dongle which you can either plug straight into a USB and get a USB connection to it, or they have a little dongle which takes the USB and just turns it straight to a UART, so then you can connect directly to a external piece of hardware, like an embedded STM or anything that supports, serial. I mean, it's quite trivial. So all of the software that we've written that connects to this device, not the stuff that necessarily generates the interface, is all written in Rust. And so that's what, I mean, I'm not going to go into a lot of depth about that today, but I mean, the punchline, which I have at the end, is that for me, the killer thing about using Rust for this project, other than I really like the abstractions, which is what I'll talk a little bit about in a minute, is that I developed it all on here for about a year and a half, nothing else, didn't test anything anywhere else. It was all just driving on here because, you know, I don't use anything else. So I used some Linux VMs for my students, but to be honest, I quite like my Mac. I don't use Xcode, just, you know, just at the prompt with Clang and stuff, and with Rust. And when I ported it to the Raspberry Pi, to Windows, that's the only two platforms so far. We haven't done it because sound is not so great on Linux. 2 days, I think, maybe, overall. With, you know, it just, I really didn't have to do very much. You know, there was a few things that didn't work, you know, particularly the audio drivers. You have to build by hand, and it's all you Rust, you have to point it to it and stuff and things. But it was pretty amazing. I was really impressed. And, you know, the greatest thing for me about Rust is Cargo, and the package manager is just amazing. That being said, I went to build the demo yesterday, and of course I've installed the latest version of Rust for other reasons, and nothing builds anymore because of all the packages are out of date. And so that is still a pain, but it's a lot better than using C++ without a package manager and building everything by hand. And I mean, it's crap, right? It's still crap. And even, I was just working with someone just the other day looking at helping them with a C++ app that they got, and we started to use the Microsoft C++ package manager, which I didn't know about. And it would only install 32-bit binaries on a 64-bit Windows machine. So I still haven't, you know, it's still not great. Whereas the Rust one's amazing. So I would say that. And I use Haskell a lot. And so I use one called Stack. I know people there's another one called Cabal, and I'm not going to get into the political arguments of that. But it's still pretty amazing, right? And the way that it puts everything, silos it, it's just great. I just want I've heard the person's here who develops it, but thanks, because it's really great. So, cool. Anyway, so we're going to go back in history just for a little bit, just to talk, because this is more of a talk about how I benefit and what I find I like about Rust and why I use it. So hopefully you can guess where I started programming. I'm quite old now, but you know, I haven't had my BBC Micro for a long time, but my brother and I used to fight over it, and he makes films now, so he doesn't do any of this stuff, you know. And but I did a lot of this. I loved it, just typing in code for magazines. You know, I'm sure we can all say, you know, the history. And obviously at some point, typing in BASIC was not enough, and so you could do inline assembler inside the BASIC interpreter, pretty cool. And 6502 was great. You know, this is where I all started. It's why I went to university, not until I was a bit older, but it was. And of course, actually the first programming language I used at university was Lisp, which I still love to this day because of its lovely braces. But anyway, it's bizarre. But of course we did this. I did a lot of this. It was a you know, computer science and maths degree. We had Solaris machines. We did a lot of C, you know, programming in C. And I'm not going to deny, I still love C today. You know, it's an amazing language. It has lots of flaws, and we wouldn't design it the same today, hence Rust, I suppose. But I still love it. Okay, and then I went and left after I finished my PhD. Obviously, I did some scripting. I still mostly do Bash. I'm not really a Python person, but anyway. I did my PhD, and I did Haskell completely. And so this is, I just want to come a little bit about this, the reason I'm putting this up. And I still use Haskell today. I still love it. And you know, it's, I suppose, the alternative to Python or whatever I use it for, those sorts of things. But of course, I worked in industry for 15 years, and yeah, I used this language. And you know, for a long time, I really thought it was amazing, and I really liked it. And you know, I'm not going to deny that. You know, I was a bit naive. I don't know. I just, you know, there's some good things about it. I felt cool that I could do template meta programming and, you know, outsmart people. It was stupid, but you know, I did. But and I also did some of this stuff. I mostly worked in a graphics group in AMD for 15 years. And I was involved with this, which has its own things. I'm not going to talk about these things. And then, of course, I discovered NPM. I admit that I discovered NPM before I discovered Cabal and Stack. I couldn't find a Stack logo, so I put the Cabal one. This is the Haskell package manager. And I hadn't done any Rust at this point. But I was back at university, and I was working in this domain. And I was pretty frustrated, to be honest. It, you know, it's a bit like fitting a peg into a round hole, right? It's a bit. Apparently, this is. I actually used this one because apparently this was from a Brexit website. This is how some people perceive the UK and the European Union. Think lots of expletives about now and swear words and what you. Yeah. Anyway, but this is a bit like C++ and Haskell, right? The two things are counter to each other. Many of the abstractions I think in Haskell are really important. They're really interesting. I don't want, there's lots of extensions and GDATs, if you're, GADTs, which generalize abstract data, which are all great, but they're a bit of an intellectual exercise in showing how smart you are rather than whether they're actually that useful. And there's debates about putting them into Rust and stuff, but whatever. At the same time, Haskell does provide really nice abstractions. It's very quick to work with. Just like people tell me about Python, I'm not going to make any stances against it. I like the static type system versus dynamic. So, in 2015, I came to my first ever FOSDEM. I'm just back. The friend of mine who's still here today, a colleague, brought me then with some students. And this is where I heard someone talking about Rust. I just overheard it in the Mozilla dev room, knew nothing about it. And so this has been my journey since then. And actually, I really, really think that I've been able to kind of fit that square peg into a round hole in some sense. Rust does that really well. And that's why I really wanted to say thing. And it's not the borrower checker. To be honest, I'm not that interested in the borrower checker. I can see that it's great for security and all that. But to be honest, if it didn't have it, I'd still use Rust. I don't really care. I've spent 3 years actually learning how it all works and fighting it and reading papers to understand it. So that was a pain. But I don't really care that much about it, to be honest. But I admit that I don't write software for many other people than myself. So it probably doesn't matter that much to me, where I can see that it's great applications, it's really useful. The thing I would say, and I wanted to make clear about that, is that it's the thing that means I can't teach Rust to first years. In my university, I think it's just too much. I can't teach Rust to first years because it's a lot to take in, particularly if you haven't had a lot of computer science and programming experience, and most of your experience is in Python or something. I personally feel that it's too much. People, they find it hard. My students find it hard. They don't even read the error messages. You're trying to get them to look in. If they start to read those complicated, it'd be like reading the messages, template metaprogramming. They're not for the faint-hearted, and it's not for the faint-hearted either. I mean, it's just a comment, and so I don't think I use the borrow checker to anywhere the kind of power that you could use it, and it's just because it's not interested. The abstractions I'm interested in are things like traits and the parametric polymorphism that you can do over those traits and things like that, and build it up. The kind of additions of obviously the range loops, but moving those more into having nice where you can return things and get the nice build-ups of functional kind of style expressions and things. So that for me has been the bit that was missing from C++. Of course, they're putting it in, well, it's like this again, isn't it? They're putting it into C++ somehow. And I find myself writing more C code than I do C++ now because of that problem, right? It's just so complicated and it doesn't really seem to fit that well. Anyway, so that's what I was going to talk. That's an aside. I want to talk about it. So I ended up using Rust. So back to the main part of the talk, and so here is a diagram that comes from this guy called Thor Magnusson, who's a famous musicologist, stroke computer scientist, stroke musician, who's a professor at Sussex University in the UK, and he describes an instrument to look something like this. So you've got this kind of the sound engines here, the sound production things. You've got your synthesis, whatever over here, whatever is creating the sound. And you've got this gestural control here, which is the interface that I showed you, the bit where you're performing interaction with the instrument itself. And obviously there's feedback. There's audio feedback coming from here, and there's hopefully haptic feedback coming from the interface itself. And really, I've kind of completely separated. I don't really think they are separate. I'm not trying to argue they're separate, but it's much easier, just like discretizing examples in itself, if we separate those two things out. And a lot of my work has been looking at that, dividing that line. And of course, the mapping then becomes a serious problem. And it's not one that's that easily solved at this point. So you'll see I have a whole, and I'll talk about just at the end, a whole Rust-based system, which is purely on this side of the world, which is just doing synthesis, DSP. It actually integrates this language called Faust, which is a purely functional language for DSP. Just it allows you to write DSP graphs in a functional expressions, just a very mathematical. It's really nice. We've got this little it generates C++. I've modified it so it generates Rust now, and it's just generates effectively a trait with some simple methods for initializing it, and then a function to ask for n number of samples. It's not particularly difficult. All the smarts is done in the Faust compiler, which I don't have anything to do with. They're all based in France, and super smart mathematicians working at a conservatory, which is kind of slightly odd. But anyway, and a lot of this here has been building physical interfaces, but using Rust to interact with the physical world. Okay? And I'm not going to talk about it today, but we've also got an embedded platform, which is all hardware, which is based on STM or ARM-based microcontrollers, mostly M4s, and stuff that we use to connect to the physical world for actuation and sensing. And I did develop some of that initially, started doing that in Rust. I started working on that, writing, from bare machine, writing it up. But I got to be honest, after about a year, I kind of gave up and I've just write it all in C now, just because of the code is really simple. It's not very complicated. And we use ST chips and they provide reasonably good libraries. And so there was just a lot of work. And I know there's some brilliant work going on. And I guess when that's got to maturity, that'll be great because I can just start off and I won't have to do all that work of getting the registers to map and all that. So I'm going to put my hands up here. I wish I hadn't had to go back, but I chose just for practicality reasons to go back to using C for speed of use. And I think that's really my message about my use of Rust, is that where it's been amazing is that, you've got a credible ecosystem, even though it's not that old, and it works mostly across most platforms I've tried, and, it can be packaged up. It's really great. And that is a bit more tricky on the embedded world today. Okay, so I probably won't talk too much about this, but if you imagine that we've got an interface like this, so I've got this whole system where you describe them in terms of extended SVGs, and you can draw them or you can write them in a little domain-specific language, which I'll show you in a second. And you can mark them up to say whether these are generating, what kind of gesture you can do, whether they're generating something called MIDI or OSC, which is open sound control, just a way of communicating standard communications. And you take these SVGs and then you run it through this system up here. So this is, it's a domain-specific language. It's actually an embedded domain-specific language, although you wouldn't know because I've embedded it in Haskell. So this is the point where you can see the different things with Rust coming in, I think using it where it makes best. One of the things I've found limiting at the moment, well, one of the things that Haskell is incredibly expressive with, that you can embed a domain-specific language in Haskell and kind of rework the syntax. It's not Racket, so you can't completely rewrite the syntax, but using this thing called template Haskell, which brings in template metaprogramming, but we won't go there, but it's quite nice at being able to define your own syntax. Not completely, you have to borrow some Haskell syntax. And Rust, I've still found that because of it still looks C-ish in some ways, you still end up with a syntax that looks quite programming languagey, even though you can definitely embed it. So I think that's a trade-off, and that's why that top one up there is Haskell rather than Rust. And it's not, performance is not critical at that top one. It's not doing anything. This one down here is doing path tracing and rasterization. I'll show you the pipeline in a minute. So performance is important here, and it wouldn't be so simple in Haskell. I mean, it's still offline, so we're not doing real-time rendering or anything like that. And so you could probably get away with writing in Haskell, but it just didn't feel natural to me. Much better fit with Rust. And there's also this amazing library called Lion, or Leon, Lion, I think it is, which is a 2D path rendering library, which I've modified slightly, but mostly I've used it out of the box, and it's just a wonderful library developed by this guy, Nicholas. And again, depending where we're going, this is all offline and generating, this generates things for what's called a Roly Light Pad, which I'll show a picture of in a minute, which is a little embedded controller which has a touch-sensitive interface with 15 by 15 LEDs. And you can upload little C programs onto it. They're not C, but they're C-like. It's like a little embedded language that you can upload onto it. So here we're actually generating code, just text files that are then uploaded onto the thing. So we're not doing any real-time processing or handling. So speed, again, is not the critical thing. Symbolic processing of what's outputted here, which is, I'll show you the JSON file in a second. Over here, though, this is the thing that connects to the touch sensor that I was talking about. This is real-time. So this is basically a driver. It's talking with a very low-level USB driver, and this is doing all the mapping from the rasterization. Well, I'll show you what I mean by rasterization in a second, but effectively it's rasterization. And here, so performance is critical because, we're actually, this is running live with a musician playing it. All the processing of when you touch something, mapping it to the semantic meaning of, are you in the right place on the sensor? What does it mean? What's the action you want to perform? Is all happening in real time. And effectively, hopefully you all know that USB jitter is pretty awful particularly on Windows. and plus or minus 3 milliseconds is good. And even on the Mac, it's around 2 milliseconds, but it doesn't jitter, which is quite nice. And then you've got the latency evolved as well, of taking that. And generally on the Mac, actually, it's around recent upgrades around 7 milliseconds on average without jitter, which is pretty good. They say that you want to be between, when you perform an action to hearing a sound, you kind of want to be within 10 milliseconds. But if you think that it's taking 7 milliseconds to guarantee that you're going to get a thing, you haven't got that much space to do any computation on the other side. You're still doing synthesis. I mean, obviously you're creating more than the same. So performance was really important here. And initially I started in C++, and it was just, C++. And, I'm fortunate enough to be in a research group, and so I get to explore things and play around with stuff. And I've been to FOSDEM, and so Rust is where we are here. And it's worked brilliantly. As I say, it's that whole stack has just been great. Okay, so I won't go into a lot of languages here, but just to give you an idea, these are the kind of things that people write in the language. We actually have a visual editor as well, so you can just use it in the web browser and draw. But I'm quite interested in what you can't do in a visual editor, so particularly programmatic expressions. So for example, I've got this little example where you have an interface of sliders that is drawn in a sine wave. And that would be pretty hard to do. I mean, you could do it in something like Illustrator or in our little thing, but you wouldn't be exactly following the sine wave. You'd probably be off, and it would be a pain. Maybe you could use a B-spline or something. And so we have a little language that you can write. This is like a stop button, and it's got a size. It's a square one for this case. And you could have something like a pad, and then you can start talking about the kind of address. So this is an OSC address. So this is effectively the message. I'm doing all right for time, aren't I? Yeah. Okay, and I'm not going to go into a lot of details about this, but you can compose them together and build up more complex interfaces. I mean, it's not rocket science, it's the standard stuff. This does, use some stuff in Haskell, like dependent types and stuff, to make this all kind of fall out, and it uses this special dependent type. We can overload the syntax, which gives us these special operators, which allow us to have arguments that aren't ordered. You can actually write these arguments in any way, and so it's more of if you're interested in type systems, it's quite fun, but it doesn't really matter to the user. You can build up interfaces, and there's a little domain-specific controllers. What's interesting here is that we have a representation. These all just map to standard SVG types, right? That's a really nice thing about SVGs, is that, of course, they're just XML, and if you extend it, Illustrator will still display it, or your web browser will still, and it will just ignore any metadata that it doesn't care about. I mean, it's great, and obviously nothing to do with me. People were doing this for years. It's just really handy, particularly because this is kind of a graphical thing that users can see their interfaces and things like that. So it works quite well. And obviously we have things like this. What I didn't realize when I started off doing it, I should mention that, I mean, this has nothing to do with Rust or anything, was that initially I just used these 3 standard SVG types, which aren't using paths, right? They're not doing B-splines or anything like that, or any kind of thing. And it's really easy to map. If you imagine, well, particularly if you know anything about rasterization and tessellation, once you take this shape, you triangulate it, I'll show you what it looks like in a minute, you can then rasterize it into effectively an array, and you just get a bitmap of where people touch, right? Because it gives you a kind of mapping from a position on the screen to a point in an array. And once you've got a point in an array, of course, you've got a pointer to a class and, or whatever, a data type, and then you can perform an action, and you get effectively order 1 lookup, for your touch, which is really important. But it turns out that actually, because we're doing tessellation, which I'll show you what that means for people who don't know what that means in a minute, is that you can take arbitrary paths. And so people could start to draw weird, they're still vector drawings, so they're not completely weird, shapes for their interfaces. That all works brilliantly. Of course, the difficult part is then to recognize gestures. Because, if you've got some weird curve like this, how do they want to interact with it? Is it following the path, or do they want to interact it with, multiple fingers, things like that? And so I still haven't solved that problem yet. We're working on that, and I've kind of got a bit of a mapping, but it's still something to work out. So this is the SVG that's created. We won't worry about that. So this is where Rust really plays its key role in this pipeline. So I don't know how many people are familiar with the graphics pipeline. Yeah, so quite a few. It's great. So hopefully you'll realize that this is effectively a graphics pipeline. You know, my background's in graphics, and so I do this. So effectively we take these shapes up here, and what you do if you're rendering a 3D game or a 2D game, particularly if you're going to run it on a GPU, is you take some primitives, some shapes up there, and normally they'll be described in terms of triangles. So this phase would have already happened. You'd have a mesh, and you just render that to the GPU. And if you haven't, you'll do this phase. So this phase is basically shape tessellation, which basically takes an arbitrary shape. I mean, it can't be completely arbitrary, but as long as it's described mathematically, either as a B-spline or as a standard geometric shape like that, and you divide it into triangles. Okay. So modern GPUs, of course, support this actually in hardware as well. So you can normally you'd send it a triangle, and then maybe you divide that into more triangles, so you can increase the resolution without having to send too many triangles in the first place. But we're not interested in that. What we really do is we have this shape assembly phase. We label it with a number here because we want to have a unique ID when it comes into the system itself. We tessellate it, and this is where Lion comes in. So I'll just give you the little thing here. He's done all the work, hard work for this. There's some really smart work. This is all the stuff they're doing for the web GPU stuff and things like that, and related, you know, in the 5. I don't know if he works for Mozilla, but quite a few of the Mozilla team are working on this and related things. So we tessellate, we generate basically a set of triangles, and then you have this phase of rasterization. So this is the bit in the GPU where they're actually generating the pixels. You know, they've gone from these geometric shapes, effectively a triangle, and they generate a bunch of colors that sit on the thing. The observation here is that we don't really care about the colors, because all we want to do is generate a lookup table from the thing. So we just write out our number that we generated at shape assembly. And I'm using shape assembly because they call it primitive assembly in the graphics pipeline, so it's just a bit of a play on that. It's just really assigning a unique number. Okay, and so you can see that we've just generated this lookup table, and clearly this will be the size of our device that we want to target, whatever that might be. Okay, so I'll move on quickly. This is what it might look like when it's tessellating. Obviously, tessellating squares and rectangles, or rectangles and triangles with trivial. It only becomes complicated when you're doing non-square shapes or rectangle shapes. Actually, circles are pretty straightforward. It only really becomes complicated if you have a squiggly thing like that, because you might have you want to draw a line and it will go outside of the thing, and so you have to start chopping that up, and that's where it becomes complicated. That's where a few bugs have come up in line, where they miss a point and you end up with a fat line rather than a thin line, things like that. But anyway, that's most of that's been resolved now. And this is literally what happens, you know, with your thing. And if we are rasterizing it, this is what it looked like. You know, you've gone, when you think about the size of the sensor. So this is, you know, it looks like an 8-bit retro image, you know, but it's like that. Okay. All right. So then finally we get to the end bit. We're just really, I don't know why it's done that. That would have been a nice bit of JSON, which would have shown you the, wow. I have to fix that another time. But up here you can see there's the buffer up here. So this is the buffer, which is the one-to-one mapping with it's the array basically that maps, that's been rasterized for all possible shapes. And so all you'll see is a 250 by 180 array of shape ID numbers. So, you know, if it was a circle, it would have 5 in it if it was going round and things like that. So there is one drawback with this whole system, and which I will mention, and is that hopefully you can see here, I'm not going to have aliased all these points, okay, because this is nicely aliased here, and so you kind of get this, when you look at it from far away, it will look like it's nice and round. I have to decide whether this is the in point and this is the out. And so it's potential, if you're doing very fine grained interfaces, you might get behaviors that you're not expecting. So, and I don't really have a good solution for that moment. Anyway, I'll move on quickly because I haven't got that long. This is what these two interfaces look like. This is the Broly Lightpad, this little company from London who make these overpriced box. So finally, I'm just going to finish. How long have I got left? About 5 minutes? Yeah, cool. So this is a little application I've developed. It's completely written in Rust. It's about 25,000 lines of Rust. It's 100% Rust. and it doesn't build anymore because I upgraded the compiler. But anyway, but it's actually, but it's really nice. So it uses that line, so it's all 2D based rendering, path rendering to generate all the graphics, step sequences. It uses the simple threading library, you know, and the queues and everything. And it runs really, really well. The performance has been amazing on my Mac and something. It's been really great because, you know, it was a question when we started this project whether Rust was quite ready for doing real-time audio. And I know a few people from Ableton have been exploring it. They're a big audio company. But it's just been great. And it's been a real pleasure to write it and everything. And what's been really nice, and I'll just finish up on this, there's this group, as I said, in France, from Paris in France, who have developed this functional programming for DSP, programming language, for sound synthesis and audio processing. And it's a really nice, it's very mathematical, so if you're interested, if you're good at DSP and understand it, it's a brilliant place to start because you're almost writing the DSP equations and stuff and things, you know, and it has delay lines and all that sort of stuff. And as I said, you write something that looks a bit like this, and so very simple code. If the stupid thing wasn't wrong, you can see that there's a simple little oscillator. You can set the frequency. And the only thing that I don't like about it is that they've kind of assumed that you have this little kind of web-based interface or little GUIs that they generate for interacting with it. And so that's okay. And there's ways of linking that with C++ software or whatever, which if I went to the next slide and it was working well, you'd be able to see the C++ code. But I don't know why it's done that. Sorry about that. But you can see that if I can show, yeah, up here. So this one here, it generates these codes, and that comes from the fact, of course, I just want to go back one slide, that they have this H slider up here, which describes a kind of an interaction with the outside world. You know, it's a side effect, effectively, but it's all functional. And so they need a way of connecting that. And to do that, they introduce these variables when they generate the C++ code, and when I generate the Rust code, it generates something as well. And then they have a way that they have like this UI that you pass in, which is the thing that's controlling it, which actually has been a real pain for us because when you build up an audio application, that's not really how you want to pass around your data. You really want to separate it as you know, the UI wants to run in a completely separate thread that isn't real-time dependent, whereas the audio thread has got to be, you know, real time, doesn't want to be. And so it can miss control signals because it might not look at the queue because of time things and everything. Whereas this has kind of all got it fixed in. So what I ended up having to do was, sorry about that, it's really annoying. But basically, if I slide over to here, you'll see that there's these functions here. So when I generate the Rust code, you basically describe a JSON file which describes the variables that you want to change, and then it generates the Rust code looking at that, and will generate just a bunch of setters and getters. I mean, fairly straightforward. There's nothing smart about it. It's really very simple code. It just has a simple strut plus a simple implementation. The implementation is initialize the audio process, the synthesizer or whatever variables need to be initialized, and then it has a compute function that you call for how many frames you want. So maybe you've got 64 frames that you need, and you just call it, and it's a simple loop. The really nice thing about the Faust compiler is because it's the way it compiles is that there's only a single outer loop. There's no nested, even though you might write it with recursion inside it, it can propagate it all the way to the top, so you end up with a single loop, and so it's incredibly performant. And of course, you know, LLVM can rip through it and optimize it really well. There's no aliasing, there's nothing. So it just, the code it generates is great. And so it's a really nice interaction, and it's benefited that Rust was written in LLVM because I now just generate from LLVM because the Faust goes to LLVM as well. So that's been really great. And you know, another great thing about Rust is that it chose to use LLVM, which I love. You know, GCC is the haunt of my life. And anyway, so that's it really. Just wanted to say, and I just, yeah, I suppose the punchline, I already gave it to you, was that it was really brilliant. The package, that's the thing for me about it. Everything else I love in Rust, I would use it all the time, but Cargo it's just been the best thing. You know, and NPM, you know, well, JavaScript, hey, I still quite like JavaScript, I can't deny it. Anyway, that's it. Thanks.
Questions, and just to remind you, we only have the one mic, so if you could repeat the question.
Okay, yes.
So if you have any questions?
hardware for like lasers and stuff like that. Is there any kind of overlap between those sorts of visual outputs and the audio outputs?
So the question is, in Rust there are some other work going on, with particularly in video and audio and image-based control systems. Is there an overlap with this work? I guess there probably is. I must admit I'm not that familiar with them, and so, but I don't see any reason why there wouldn't be. There's some novel work in this, but the Rust part of it probably isn't that novel, other than I think it's a great application for Rust. You know, we wanted performance, but I really care about having some of those high-level abstractions, and that for me is the main. That's why I would encourage people to use Rust. Again, I know a lot of people, and I hear people at my university, particularly people in the security groups, talking about Rust because Microsoft's now talking about it. You know, and absolutely, that's great, right? I completely see that. It's just I fall asleep when they start talking about it. So it's just not me, but that's just a personal thing, and not a criticism of Rust at all. In the laboratory, I mean, it's amazing. It's just not my interest. So, but yeah.
So unfortunately, that's all the time we have.
Okay.
You'll probably be available in the hallway for more questions.
Yeah, if my cold, actually I feel a bit better now. I think I just got a sweat on, so it's good. But yes, yeah, definitely.
Great.